Continuing on with homework number 14, here's problem 2. We have this crank slider with the dimensions of 275, 475. We have in this position right here, we have it at 60 degrees at theta A and 45 degrees at theta C. And it's got an input, this is we call this the crank sometimes. It's got a crank angular velocity of 4 radians per second clockwise, and we want to find the velocity of this piston at C using the ICR method. So here you go. Here it is, my written out version of the thing. And I don't know if I did a very good job of making that 45. I could have, and maybe it would have been smarter to use my, yeah, you can see that it's almost like 60 degrees, right? That's close to being, this right here would be 60 degrees. Right there, it's like, yeah, that's damn close to being 60 degrees right there. It's something less. Maybe it's like it was like 55 degrees, something like that maybe. But anyway, this is supposed to be 60 degrees, and it looks more like 45. So it might be a better idea to actually sketch out these things. First thing that we want to do, though, is find the velocity at B. And that's just going to be a pure rotation of link AB. So that's the idea, is these things share the same velocities together. So I'll write this guy out here, and I'm going to make him the correct. I should have drawn the thing the right way the first time, but oh well. So starting out with this guy, here's a velocity analysis of link AB, and a lot of times that's what I'll do later on when I'm trying to when I'm doing the acceleration stuff. So we go to the velocity analysis. Velocity. Maybe I'll. All right, I guess I'll write out there. I can't remember how I usually do it. I usually don't write out so long. Analysis of AB. Right here it says velocity analysis of AB, and I see that it's rotating at this angular velocity right here. It's got this length right there. Its velocity is going to be perpendicular to it, right? So its velocity, the velocity of B, that is going to be that way right there. And by the way, just using the triangles that are available right here, we can see that this angle, theta A, is going to be the same thing as this angle right here, theta A, right here. And the velocity of VB is simply going to be omega AB times the length of AB, right? So 4 radians per second times 275. So 4 times 275, 275 times, boom. So we get 1,100 millimeters per second. Great. So now what we need to do with that is to transfer it over onto this guy right here. And like I said, I needed to do a better job of this. So I will, I don't know, I'm using up a lot of the page, but I guess I'll make it down here. I need to put it in a spot where it's not going to, where there's going to be plenty of room. So we've got to be careful not to try to be too conservative with the paper. I want it to work out pretty well. All right, so here is what this thing is going to move. And we know the line of action of C is this direction. So its ICR is going to land on a line that's perpendicular to it. So it's going to be a line that's like vertical. And for this one, okay, so I did a lousy job of this. I didn't plan this out once. So let me plan this out again. All right, so I could kind of see it coming. I didn't do a sketch. I should do this on scratch paper and then do it live here. But I was trying to think. Well, what we will find in many of these parts right here is that the ICR is going to be the projection of this right? Because it's gonna the ICR is gonna land along this line right here. It's gonna have with the intersection of that right there, right? So it's gonna be like up there. So I need to give myself plenty of space, and I need to kind of like forecast that a lot. So let me give myself some space right in there and some space right in here. And then I know that this is going to be a 45 right here, okay? So I don't know if maybe I have confused people by what I've just said right there, but this is the location of the ICR, right? Because the velocity is hard to see how that's going to go. It's going to be perpendicular to this line right there, right? So the velocity I just found right here is going to be right there. This is the velocity of B. And this distance right here is going to be R. This is the ICR. RB with respect to the ICR. I like to have this line too. Right? Now, I'm also going to need to have this one here in a minute. That guy, which is going to be the R of C with respect to ICR. But even before we start with this, we could figure out what direction this thing is going to rotate. It has to rotate in that direction, right? By the way, make sure that we see that that right there is perpendicular. It's going to rotate in that direction, and therefore this is going to move in this direction, right? So before we even got any values, we could figure out what the direction of the velocity of C was going to be. Now we have a geometry challenge though. But we know a couple of things, right? First off, we know this angle right there has to be 45 degrees. Now, don't get confused in thinking that this line is perpendicular to this, because it's not. But we do have, excuse me, this guy right here of being 45 degrees. We also know this length right here. That length is LBC, which was 475 millimeters, right? So 475 millimeters. So we have two pieces of information. We need a third piece of information. Okay, so this can be a little nerve-wracking trying to get this part right here. So this is like a geometry challenge right here. But we can split this guy in half right here. And we know this angle, right? So you can see that it's coming all the way. We know that this is 45 degrees. And we also know the angle of this. Oh, that didn't do a very good job horizontal right there, because it's not aligning with these lines right here. So this is horizontal right there. Okay, and it wasn't really that much different. We also know this angle right there is 30 degrees. Okay, so what is, yes, we know that, right? So we also know that this is 60 degrees right here. We didn't actually need to do that 30-degree one right there. But you could see that this is perpendicular to that. So there's that 30 degrees and the 60 degrees. So we know the total angle inside this triangle is 105 degrees, right? It's 90 plus 15. There's the 15 right there. So I have to break these things apart, right? So that's the challenge of the ICR, is the geometry quite often. So we can find this using the law of cosines. We can use the law of sines. actually we can use law of sines because we know two angles. We know the 45 and we know the 105. So now we can use law of sines, LOS. So the law of sines says that this is length BC is equal. We're going to say, okay, so once we know, all right, let me take it another way. Once we know two angles of a triangle, we know the third angle, right? And so the third angle right here, I'm going to call that beta. Beta is going to be equal to 180 degrees minus 45 degrees minus 105 degrees, right? Because all three angles have to add up to 180 degrees. So we can find 180 minus 45 minus 105. So that ends up being 30 degrees. And any normal person could have figured that out anyway. Yes, because this line, that was 60 degrees. This is vertical. That had to be 30 degrees. Okay, so anyway, if you want to find, now we have to find RB with respect to ICR. So it's going to RB with respect to ICR divided by the sine of 45 degrees is going to be equal to LBC, I'm going to write it in a symbol, divided by the sine of beta, which is 30 degrees, right? So we could find that RB with respect to ICR is going to be equal to sine of 45, sorry. Sine of 45 is going to be multiplied up here. Sine of 45 divided by the sine of 30 times LBC, which is 475. So we're going to get, I'm kind of like making a mess out of this thing. It's not my best work. Yeah, whatever. Sine 30, sine, you divide the thing out and you multiply by 475, and we get that it's 671.8 millimeters. Okay. Now, while we're at it, maybe we can also find RC with respect to ICR. And that's going to be the one that's opposite that is the sine of 105. And might as well be the same thing, right? Might as well be that 475 divided by the sine of 30. So we get RC with respect to ICR. It's just going to be sine of 105. And you got to be careful sometimes. That could be a negative number. Let me double check. 105 sine. No, it's fine. Okay. And the sine of 30 times our 475. So we get 105. I already did that. Up. Take 30 and take the sine of it. But of course that's just 0.5. So divided and then 475 times. And we get it's 917.6 millimeters. So what we're able to do here is we can find, from the velocity of B is equal to omega A, well, not AB. I didn't even label him yet. This is omega BC, right? This is length BC, because this is B and this is C right there. BC times RB with respect to ICR, right? So just this distance times that omega gives us this velocity. We want to find BC, so we take velocity of B divided by RB with respect to ICR. So we get omega BC is equal to 1,100 from up here divided by 671.8. So we get omega BC 1100. I get that it's traveling at, it's going to rotate at 1.638 radians per second, and that's going that way, omega BC. And let's double check that with our previous solution. All right, so this was what we got from, there you go, 1.638 is what we got using the 3-diagram method from the previous homework. But this seemed a lot harder, right, on one level because of the geometry. But here's, we can get the velocity of c. Once we know this, it's not too bad, but we want the r of c with respect to ICR, or 1.638 times our 917.6. And we get 1,503 millimeters per second. And let's compare that to what we just got in our previous homework right here. Boom, right there, right? 1,503, going to the right. That was our prediction. So we got the answers. We got the answer. The velocity of c is equal to 1,500 millimeters per second that-a-ways. And we are done. I know, it was tough. Hopefully I didn't confuse you with my geometry on the fly. I should have planned it out a little bit better. It was really all about making enough room for this diagram, right? So I totally forgot what this one looked like. This is a particularly difficult one, I think, because of these angles. If it wasn't, it would even be kind of worse if we were picking some, things that angles that get even closer. As this thing, if this got smaller but still was there, right? It didn't collapse completely. That could make it a little bit more challenging. But going through the logical geometry of the thing, you'll be able to find it. ICR is generally going to be easier, I think, even if this one wasn't.